Thanks for coming, everybody. So it's been kind of enormous number of SLT talks this week. And if you've been to some of them, hopefully you felt like some of the presenters looked like smart people and they were saying interesting, competent looking things. But the job of this talk is to answer the question, well, so what? Okay. But first, just a very brief recap of what SLT is about and the aspects of SLT that are most relevant to the answer to the question, so what? So SLT is like, in 5 words, learning theory without Laplace approximations. Okay? No explanation. So in more detail, I mean, the first quantity that we took from Watanabe's work and tried hard to estimate in larger models was the local learning coefficient, which can be thought of in various ways. So it's a geometric invariant, but it can also be thought of as a measure of model complexity. And a lot of what we did over the last, particularly in the first year of the research agenda, sort of starting in 2023, I mean, some of us have been thinking about SLT since like 2019. But the kind of agenda that you're seeing presented here is sort of like, in many ways, a 2-year-old thing since the middle of 2023. So we spent a lot of time taking the LLC, figuring out how to estimate it as far as we could, seeing that these estimates made sense, and then seeing in larger models what those estimates seem to be correlated with, especially over the course of training. And that's what we call developmental interpretability. And we've done that now in a bunch of different models and get sensible and interesting answers. You're probably sick of seeing this quote, but like, it's great. So you'll see again. So Watanabe, in the very first page of his book, has this comment. And when I opened this book, in 2019 sometime, and saw this, I was like, what does this mean? So this was a big reason why I became interested in SLT. Just this idea that singularity theory, which was something I studied for many years, could be of any relevance at all to statistics, let alone be really quite central to understanding what information in a statistical model was. What we're now trying to do is take this idea and push it a bit further to use the idea that if you want to understand the structure of knowledge in a learning machine, that this might be related to structure and singularities. Now, the structure of knowledge seemed like it might not be a very easy thing to formalize, just like the structure of an algorithm has some intuitive content, but isn't the easiest thing to formalize. And Will spoke about that a bit earlier in the week. The structure of singularities, on the other hand, I mean, we have lots of answers to what that might mean. So in some sense, we know a lot more about the structure of singularities than we do in some formal sense about the structure of knowledge or algorithms, interpreted in some precise way. But if you believe this, that opens up a path to interpretability, right? Because SLT says you can relate geometry to core quantities in statistics. And if you can learn more about the geometry, maybe you can learn more about what the statistical models mean and what they're doing. And so this is the simple idea that we've been pursuing doggedly for the last few years. And hopefully you buy that the results we're presenting this week with susceptibilities and influence functions show that, on models between 1 and 10 billion parameters now, we're starting to see like real evidence that this is true. You can actually find interesting structure in models using these kinds of ideas. Okay, so I'm going to run briefly through some of the talks because not everybody was at all of them. So I'll say 1 or 2 words about the SLT talks that took place this week. I mean, I want to flag that, obviously Timaeus is doing a lot of work on SLT, but my colleague Susan Way at the University of Melbourne, now at Monash, was involved in the very beginning in SLT. Still people at the University of Melbourne, nothing to do with Timaeus working on SLT. This is not just a Timaeus thing, right? Now at the UK ASY. So there's a broad community of us working on SLT. And of course, Watanabe and Aoyagi and Hayashi and other folks in Japan. And increasingly, Jai Li is doing some interesting work on SLT in Germany. So there's increasing number of people doing this kind of stuff, and I'm representing or trying to represent the broader ecosystem. So Lucius had a very interesting talk earlier in the week relating SLT to algorithmic information theory. I spoke about our work on susceptibilities, which is an idea from statistical physics that we're trying to apply in interpretability. Jesse spoke about influence functions, which is closely related, or an instance of susceptibilities, doing that with an SLT lens. Andy spoke about the relation between susceptibilities and relations. George showed some nice pictures of the rainbow serpent, which is a sort of picture of the data manifold from the point of view of a language model as interpreted through susceptibilities. Simon's given a couple of great talks on the foundations of SLT. And actually, I couldn't make it to the first one, so I don't know if jet schemes came up, but jet schemes is another very interesting foundational aspect of the interaction between geometry and SLT that is going to be important. We heard a talk from Edmund and Einar about the addressing some of the theoretical constraints in the kind of existing treatment of MDL using some of the mathematical ideas that Watanabe introduced. And experimentally, sort of an interesting observation, I'll have a slide on this later, that you can relate the effect of quantization on a model to the LLC, which is a sort of nice relation between this LLC estimate and a kind of more ad hoc, informal notion of the amount of information in a model that's widely used. Now we had Rowan and Dan present on SGLD and various issues and opportunities in connection with SGLD for improving LLC estimation and some of the limitations that go along with it right now. Will said a bit about the idea of trying to, in a case where we understand what algorithms are, namely Turing machines, and have some intuition for what the structure means, trying to take that understanding, translate it into a geometric setting by creating a lost landscape where critical points are Turing machines. Billy was then leading on from Will's talk, presenting some more quantitative analysis of particular examples in that setting and explaining some interesting new tools for interacting with this geometry. And then Ben and I spoke about Ben's thesis work. So Ben's just wrapping up, well, it's about 6 months more in a PhD, where he's been working on correlation functions, the setting of SLT, and using resolution of singularities to explicitly compute asymptotic expansions of correlation functions. So that's of interest both in SLT and for things like the neural network QFT corresponds. And just now in the last session, some of you saw the preliminary work where we are taking SLT and applying it to reinforcement learning. You can actually see that the kinds of phase transitions that we were detecting with the learning coefficient in supervised learning can also be seen in the learning process of agents in simple environments. By the way, I have fewer slides than I need for like a full hour, so really ask questions. Okay, so I want to group these into a couple of buckets. So the first bucket is susceptibilities. So I want to make the point that, A, this is kind of like a sensible natural notion, very close to what you use in physics to infer structure in materials. We're applying this in neural networks, and it seems to work. And the second point is that there's a pretty sound, I think, sort of theoretical basis for using this as an interpretability tool to the extent that this sort of proposal, hypothesis, thesis is true. So structural Bayesianism is the thesis that the internal structure in learned algorithms in learning machines is related to geometric structure. Okay. I mean, that's not a fact. It's like pretty plausible from many theoretical angles, and we're accumulating more empirical evidence for it. But this is the motivating idea behind what we're doing with interpretability. Okay. So what? Right, so we wrote this position paper. You can see the author list up there. We wrote this position paper to start to answer this question, right? Like scientifically, this all seems to be going pretty well, but this is not an entirely scientific enterprise, right? The goal of this research is to make breakthrough progress on alignment. That's the mission of Timaeus and the interest of many of the other people involved in working on SLT. So what we tried to explain in this position paper was the idea that if we get a better grip on understanding how structure in data becomes structure in models, then for one thing, we'll have a better idea what models are doing. And for another, we might be able to direct that process more deliberately. Okay. I want to spend a bit of time talking about this figure. The reason I want to spend a bit of time talking about it is I think it illustrates kind of way in which you can use the ideas of SLT to think new thoughts. Right? So obviously, like a body of mathematical knowledge or empirical knowledge allows you to prove theorems, allows you to do experiments, but it's also useful in just giving you a mental frame with which to approach a problem. And I do think SLT is at least as useful in that mode as it is in these more technical, precise modes. And so here's an example of how you can think about alignment and use SLT as a kind of tool for thinking about some things that might otherwise be surprising. Okay, so I'll come back to this figure in a moment, but let me just describe the way you might attempt to get a model to behave in a particular way. You just collect a lot of data that you think points at doing things in that particular way, right? Many examples underlying which you think the predominant pattern is do this thing I want you to do. Maybe you can't actually articulate exactly what it is that you want to be done, but that's the modern machine learning paradigm, right? You don't actually have to be able to precisely specify the behavior you want. You can collect lots of data which seems to have as its underlying common pattern, do the thing we want. So deliberative alignment, OpenAI's, as far as I understand, best current take on aligning frontier models is exactly like this, right? So we listen to Boaz Barak, for instance, talk about his vision for how deliberative alignment should work. It looks like, I hope I don't misquote him, but he has a blog post on his webpage that you can go and look at, which I like very much. Something like put the Constitution in context. Right? If the model is, I mean, you approximate that in some way. If the model is learning to act according to a long list of policies and rules and represents that faithfully in its deliberative process, then this is going to eliminate many of the problems that you might face deploying these systems widely. That's, I think, quite a sensible take. However, I mean, it has some issues if you think about the underlying learning process that you hope translates that very exhaustive specification into a parameter and into behavior. Okay, so I'll come back to the picture. So we collect a lot of data, we put a lot of stuff in context, we think it points at some unique good behavior. That's here. What does it mean for a bunch of data to point at a good behavior? Well, what we want to say is that that behavior is optimal, right? That's the global minima for the loss landscape that is associated to that data. So in this picture, I mean, the curve here, you think of that as the population loss. So the average negative log likelihood associated to some particular model and some collection of data. And any point in V, or in particular the global minima itself, little v, is meant to represent the behavior we thought we were targeting when we collected the data. And if we train long enough, we should hit that. Right? That's the global minima, and modulo getting stuck in saddle points or some other lack of understanding of how the global loss landscape of S2D looks. This is the thing that we're pointing to. Of course, we understand that there are other local minima that the model might encounter on the way to the global minimum. And so a typical concern, which, for example, comes up explicitly in Jeffrey Irving's approach to debate, when you're trying to get these debating agents to converge to something which represents the Nash equilibrium of scalable oversight by debate, one of the obstacles is that you might not reach the Nash equilibrium because the parameterized model you're hoping to reach it gets stuck at a local minimum. Okay, so typical concern expressed in connection with the impact of optimization and learning on realizing some proposal for alignment is getting stuck in a local minimum. Okay. So far, this doesn't involve SLT. So let me bring kind of an SLT lens to this situation. The SLT lens, which Jesse was talking about at the beginning of the week, is that there are two important quantities from a Bayesian point of view when you're talking about Bayesian learning, and therefore potentially also SGD. There's the loss, but there's also the complexity. This is not an SLT perspective. This is model selection sort of 101, right? Just depends what kind of complexity you're talking about. So, the BIC, or for a long time, we've understood that selecting between regions of parameter space, selecting between classes of models, comes down to a trade-off between the degree of fit to the data and the complexity of the model. In this particular instance, the two models, so to speak, on offer are this class of parameters, which sort of do the thing you were hoping or pointing at or thought you were pointing at with the data, and this class, which is something else, which isn't fit to the data quite as well, but is simpler. So the way I'm indicating that it's simpler in this picture is that that local minima is flatter. And that's maybe it's a bit too small to see, but the idea is that this is greater loss. It's higher in the loss landscape, but it's flat. So that's lambda is small. Okay, so the free energy formula, which is this tool for thinking about what happens in Bayesian learning, both quantitatively but also qualitatively, says that you should not be surprised if for small numbers of samples, and therefore perhaps also earlier in training, this higher loss but lower complexity solution is actually the optimal one, in the sense that the Bayesian posterior concentrates there. And this is different to the situation where you don't take into account complexity in a way that varies around parameter space, because if you don't do that, then you think that the posterior is just this big blob that is steadily becoming more and more Gaussian around the MAP. Right? But in the singular case, where the complexity can vary, this is not true. And this solution could be preferred for some number of samples. Okay, so to come back to the alignment context, if this is what you're pointing at, and this is a simplification, what is the content of that simplification? Maybe that's some heuristic that is undesirable, for instance. But this is actually what, in fact, your data is pointing at if you are not at infinite n. And as Watanabe points out, he has a really lovely paper which has a section, I forget the title, maybe Simone, you remember, the one that's talking about a survey of, so he has a section talking about alignment, makes the point that, large n is great, but it's not infinite. And in practice, we do see training actual transformers on things like in-context linear regression, that models can get stuck at these simpler but worse solutions for like large multiples of the training time. Okay, so this is like an actual practical issue in concrete examples we can point to and say this happens. Okay, let's come back to Boas-Barak for a second. You stick the constitution in there, lots and lots of rules, lots and lots of edge cases. It would be a complete pain to encode all the edge cases and strict rules and all the like places where the rules are in conflict or tension. Quite complicated to encode all that. Now, maybe it's a lot simpler to encode something else, and you don't know what that is, right? You just train the model, you get something, you think, okay, that's good enough loss. Let's go ahead and deploy that. Wouldn't it be great if you could actually characterize the degree to which the structure inside the model is representing the thing you thought you were putting in? And so that's, basically where we see the role of interpretability, right? What is the content of this gap? Okay, so I'm going to spend a bit of the next 10 minutes or so going through a few of the bits of eye candy from the various interpretability talks. And then I'm going to say a bit about the second category of applications down here, which is roughly speaking, how could you prevent this from happening in the first place? That is, how could you arrange that you are directly controlling the formation of structure rather than relying in some blind fashion on hoping the structure in the data you collected points at the thing that you think when you collected it, it was pointing at? I'll pause here for questions. Yeah.
So one question is about this different layer domain. But in
neural network, you have layers of weights. Can I get the local LLC for a particular layer in the other layers?
You mean by integrate now?
Because you have posterior on all these weight vectors, and I have, say, 20 layers. I only care about the last layer because my conjecture is that for the last layer, you might have the complexity at the optimum actually smaller because you're going to learn about the patterns of the data. So your global one might be, this is the right picture, but if I zoom in to different layers, I might see for the blue, actually I have lower.
Yes, I think that makes sense. So we actually do that with LLC estimation. So not sure if it exactly answers your question. So you can freeze the weights in all the layers but one and just vary those according to a posterior that is just for that.
Or you just integrate out either way it's possible.
Yeah, that's right.
The other way.
Yeah, and that actually does seem to give some information about how the different layers are behaving differently with respect to the data distribution.
Do you see the reversal? At the blue, you might have lower complexity.
Oh, yeah. Sorry. Oh, there's another mark. Thanks. Testing.
Can you also integrate out the other layers? You have a posterior over the weights.
Yeah.
I don't know if it's possible.
Yeah, I see what you mean. I don't know. But, yeah. Other questions? Yeah.
Why don't we want to be in you? Right? Isn't this do what I mean, not what I say? Like, isn't this exactly what we want from our system?
Yeah, John and I had that argument, I think. Yeah, I think you could take the position of, maybe the simpler thing is safer. Yeah. I don't think I have a knockdown argument against that. I think my argument would be, it seems intrinsically kind of a bad situation to be in, where you collected a lot of data thinking it incentivizes V, and you end up with U, and you don't know what U is.
You may not know what you mean, but you may like it when you get it.
Yeah, indeed, you may.
Yeah.
In biology, there is a concept of survival of the flattest, which is basically preferring robust landscapes to highly specialized, very, very seemingly good ones, but not robust ones. So to me, it looks like this is a very similar situation here. Do you have any comment why or whether this might be actually a plausible way of identifying relevant spaces? Essentially, it goes back to what people have said, but I think it's a bit deeper because it's robust. U seems to be more robust than B.
Yeah, correct. Maybe hang on to that a second so I don't get feed. Yes, so robustness is a good way of thinking about this. So the last time I spoke about this, what I'm about to say was a conjecture because we hadn't been looking at reinforcement learning yet. But I think now we could just sort of flatly say that robustness of a policy seems to be actually a thing that the LLC measures. And so what kind of behaviors are more robust? Well, one way in which a policy might be more robust is, for example, well, by definition, that means it's resistant to perturbations in its environment, in the sense that it can recover from errors. One kind of error, this is putting a dramatic spin on it, you could have many, many, many interpretations of what robustness might mean. But one form of robustness we might be concerned about is human intervention. Right? So if a policy is just very, very good at getting what it wants to get done, independent of interventions or perturbations, that's a pretty strong sense of like goal directedness or something. Many people in this community have written it. So I think that's, but the second part maybe.
No, I think that was the question. So what you seem to indicate is robustness means that network is stubborn, basically will not be told what to do, which is exactly what we are a little bit worried about, that it might. But there is also another element. I think if you want V in real life as a human, you have to work very hard for that. So if you want a supremely capable juggler or somebody who does extremely high quality sports, these people train a lot to get to V, and they do deliberate training to stick in this thing. And when they're not practicing, they lose it and they land in U. So maybe it's not quite as alien as we might consider it. So the question is, maybe it makes sense to actually give them the right relation. So if you really want V, then you have to work to make it go to V by a special training program, for example.
Completely agree. In particular, it might be nice to know if you have reached V or not. Okay, so I'm going to move on to just recapping some of the interpretability results. Oh, sorry, this first. So this is how we think about the stack, at least in our approach. So based on singular learning theory, this ideas around like geometry being related to internal structure. You can try and do interpretability. Interpretability might allow you to understand, for example, the difference between these regions U and V in terms of the way the model generalizes and ground that generalization in internal structure. And then, as Daniel was very helpfully pointing out, you might then like to use that understanding to push the model in ways that have the generalization you want, or therefore the form of internal structure. Okay. So just briefly, this is one of the papers that we've been working on for a while. It hasn't come out yet, should be soon, hopefully. But Edmund and Einar spoke about this earlier in the week. So what this is showing in this plot is LLC along the x-axis and a measure of sensitivity to quantization on the y-axis. So if you take language models, this is going up to 7 billion in the Pythia family, and you think about what degree of quantization can I do without increasing the loss past some threshold, you will see that models with larger LLC are more sensitive to quantization, which makes sense. There's more information in the models. It's using like more bits of the sort of precision, and therefore it's more sensitive. So this expectation, and this is not a surprise, in fact, but what is a bit surprising is the degree to which it's quite linear over a large range of the LLC values, apart from the beginning and end of training. Okay, so there was a kind of folklore, that's a bit too dismissive. There was a practical understanding that the amount of information in a model could be thought of as this sensitivity to quantization in the quantization literature. And it's kind of comforting to see this line up with the LLC estimate, especially given that in, say, transformers, we don't have ground truth about the LLC to know when we're getting accurate estimates. This is not to say this is an accurate estimate. It's like look at these numbers on the x-axis. They're in the hundreds, and the model's got billions of parameters. So like, you don't over update or something. But like, this is one among a few indications that we can both do LLC estimation in practice for models with billions of parameters, and it makes sense.
And sorry, can I ask a quick question?
Yeah.
Oh, got thrown. Thank you. Sorry. So I just wanted to follow up on that. This is a model with billions of parameters, and the LLC is 240. Is the effective dimensionality of that system that small? So what is this an estimate of?
Yeah, that's a good question. So the estimator is sensitive to the inverse temperature that you do it at. In a way that means you can sort of, the numbers you get out of it, the scale is not something you should be paying attention to.
Just relative differences between different models using that particular estimation method.
Yeah, that's right. So usually what we do is like within for a single model over the course of training, we have like, I would say empirical evidence that the relative changes in the LLC estimate are meaningful, even if the absolute value, you shouldn't pay attention to the scale. This is a bit surprising because these are 4 different lithiums at like quite different scales. Maybe you can't read that. I can't. So pixels are too large. That goes from 160 to 6.9 billion. So the most purple one is 160 million parameters, and the yellow is 6.9 billion. Despite that fact, the LLC estimates are like very similar. So yeah. Okay.
Yeah. Sorry, could I ask, since we have time, right?
Yep.
There's this about this LLC estimation at a certain temperature. There's this picture that tuning the temperature is like noising out lower modes, lower contributors to the sort of overall algorithm or loss. And if you tune it a lot, like very high noise, then maybe you only pick up on the largest modes. To what degree is that picture, you think, is that sort of meaningful, correct, or something in these empirical?
Yeah, thanks for the question. So the inverse temperature that you put the posterior at when you're doing LLC estimation, like in theory, doesn't change the LLC you get. But in practice, it does. And when you think about what's going on when you're doing SGLD chains, you can prove. So former PhD student of mine, Zhongtian Chen, and I worked on this, and Dmitry Vaintrov has also written about the role of temperature in the posterior and what it does to expectation values. You can prove that SGLD, I mean, it's common sense. It's a bit of a pain to prove, but it's common sense that if you're only taking 1,000 steps of SGLD and you're trying to infer something about a model with billions of parameters that has in those parameters encoded, tens of thousands, hundreds of thousands of bigrams and their probabilities. Like 1,000 steps, SGLD is not magic, right? It can't give you, and you can't get more bits out than you've somehow in entropy spent. So it must be the case that if SGLD is giving you some information, it is discarding some of what's available in the geometry of the population loss. So a reasonable expectation, and what we kind of clarify with this theorem, is that what you're instead getting is something about the LLC of an effective loss associated to an effective true distribution, which is in fact truncating lower modes in some precise sense. So, for example, bigrams above a certain probability would be something that the estimation process is sensitive to, but not these very fine details. So that's a theorem. Whether or not that explains what's going on in these experiments is unknown. You could design experiments to test that, for example, by cooking up distributions with a tail of modes, like bigrams of lower and lower probability, seeing correlations between the LLC estimates and its performance on those. Those would be great experiments to do, but that hasn't. Yeah.
What's the name of the experiment?
Modes of sequence models and learning coefficient. I think I won't say too much about this. This has been advertised pretty heavily already this week. But this is what we're doing with susceptibilities to visualize what the data manifold, so to speak, looks like from the model's perspective. For each sample from the pile, you can associate to it a vector of susceptibilities. And I'll come back to this vector of susceptibilities in a moment. So maybe I'll spend just a sec saying what this is. So in this model, there are 16 attention heads. So however many components you want to pick, you get that many susceptibilities. Roughly speaking, that's something like the sensitivity of the posterior specifically for that model component with respect to dialing up or down the probability of some token y in context x. That's a real number, positive or negative. You get a vector. You can associate to the sample xy from a pile, say, just some sequence distribution, this vector, and then apply UMAP to that point cloud. You get a picture like this. So this is like how this particular model thinks about these samples. Samples that are close together, you could conjecture are computed on in a similar way. And this is an intuition that Jesse was also expressing in connection with the BIF, the Bayesian Bayesian influence functions, and the posterior loss cone. Okay, so this is a way of thinking about representing inputs in a way that's not activations, not SAE features, but these other kind of statistical physics-derived, SLT-derived quantities called susceptibilities. And we seem to see in this 3 million parameter model some evidence in that representation of internal structure. In the case of the induction circuit, structure that we're very sure is there from independent methods. And then a new structure, the spacing fin, which we can see in the UMAP and then investigate, and which seems to be genuine internal structure in the model for dealing with long sequences of spaces and somehow like orienting yourself within sequences of spaces. So this is like under the heading of interpretability, and the connection to the so what question is, if you think we're going to make impact on alignment by shaping model behavior, and to shape model behavior, you need to have some insight into what that behavior is and how it's grounded in internal structure. You need to believe that the methods for detecting internal structure, which are connected to the underlying mathematical story, actually work. Okay, so this is some evidence of that proposition. And this is it overtraining, sort of, you know, like a bit like ugly duckling, right? I wanted to show you Pythia 70 million just to sort of drive home this comment about internal structure. I mean, these pictures aren't in papers yet for the larger Pythia models. The only paper that's on the archive is for the 3 million parameter model. We're working on the paper for the Pythia models. We don't understand, I mean, there's all these interesting kind of discolorations and streaks of tokens that seem to be interesting. We don't really understand what's going on. That's work in progress. But I wanted to flag to you something that Andy talked about in his session, which is that at least one of these kind of collections of tokens that's moved out of the body of the UMAP, corresponding to a kind of elevated susceptibility, seems to be susceptibilities to some particular pattern. And that pattern is things like as well as, not only as well as, it's also such as, a few others, if I remember correctly. And we've looked at this with ablations and seen that, you know, in fact, the head that the susceptibilities seem to be saying is responsible for this structure in the UMAP really does seem from the point of view of other techniques to also be playing that role. I don't want to give the indication that like ablations are ground truth or something. I don't think in interpretability we usually have any ground truth, but like if you use another technique and get consistent things, it's probably less likely to be an illusion, maybe. Okay, this is the largest we've gone with this technique. The influence functions have been run up to 2.8. Sorry? Yeah, I think that's right. So this is one of the UMAPs from the influence functions. So it's a great blog post written by Max and Zach, Jesse, which shows you these UMAPs, and you can click around on them and see how the influence functions are distinguishing different samples, in this case from ImageNet, it seems like, by the way that the model computes it. So another indication that this posterior sampling business is actually sort of by definition and by the theorems related to the geometry of the KL divergence, but also seems to be sensitive to internal structure of the models in image models. And these influence functions can also be used in language models, and you can find more. There's a couple of workshop papers with more details that you can find in this. Okay. So I referred earlier, I sort of already sketched how SLT for agents might be interesting, right? So the free energy formula in SLT says something about the trade-off between fit to the data, or in the RL case, regret, and complexity of your network, or complexity in this case of the parameterized policy. And you might find situations like the one I was explaining with U and V, where the complexity of the policy or its relation to robustness would be something that had some behavioral meaning. Okay, so this is just showing work in progress where we're able to both derive a sort of underlying theory with theorems that extend the free energy formula and related results to the RL setting, which has various important differences from supervised learning, so this is not trivial. Extend those theorems and then apply the estimators that are derived from those theorems to estimate learning coefficients for agents over training. In this case, a simple agent is finding a cheese in the top left-hand corner of a maze with no walls. So the pixels here represent movement. So this is showing a policy that always moves to the left when it's near the top of the maze. This is showing a policy that always moves up when it's at the left-hand side of the maze. And you can see the changes in the representation, the visual representation of the policy, which sort of track with the change in the LLC estimate. So there's a phase transition at some point where the LLC estimate jumps up, and this corresponds to the development of a kind of non-trivial, more complex policy in the model. Okay, so it's still early days, but SLT seems on track to be saying the same kinds of things about agents as it does about supervised.
Yep. Just that.
Kind of what happened.
Thanks. All right. I'm sure this question gets asked. The LLC, I can make sense of it when I'm in a local minima. Is this system in a local minima throughout its training?
No.
Okay, so
What does it mean?
yeah, exactly. Help me.
Yeah. I think a complete answer to that question relies on both more empirical and also theoretical work. But I can give you the best current guess, and that is related to my answer to the earlier question about modes. So if you suppose that there are lots of structures in the data distribution which come like with varying frequencies and complexities, and think about ordering them in some fashion. Maybe it's very hard in practice to order a complicated data distribution, but in simple cases, say order them by the eigenvalue of the input-output correlation matrix. If in fact the data distribution, so if in fact the loss landscape for which you are estimating, when you run SGLD to get an LLC estimate, rather than getting an estimate of the LLC of the population loss, which is like has all this information in it, if you are in fact getting an estimate of some sort of truncated version of the true distribution, you could be at a local minimum or close to a local minimum of that truncated loss associated to the truncation of the true distribution, even though you are not at a local minimum of the population loss. And we had a paper about, title changed. What's ICL1?
Stage-wise learning is lost landscape.
Stage-wise learning in the lost landscape of something, yeah. So in that paper, there's some appendices which go into the observation that the model, this is a language model, over the course of training, there does actually seem to be effective potentials of this kind, where the model is, during training, the loss is always sort of strictly decreasing, but there are effective potentials associated to some of the simpler patterns that the model learns first, like bigrams, for which the model does in fact appear to be at a local minimum. So I'm going out on a limb here, but my current best guess is that the reason why SGLD is more stable than you might expect and seems to give meaningful answers, even though you're almost certainly not at a local minimum of like complicated data distribution early in training, is that the SGLD process is not sensitive to the higher modes, and you are at a local minimum for some effective potential, and you're getting the LLC of that.
Okay, thank you.
That is, yeah, that's speculative. Okay, let me just check. All right, I lied about having enough time. Okay, so I want to say a bit about the idea for writing structure to models, which we refer to as patterning. This is like the next layer of the stack above interpretability. That's what we want to now use the progress in interpretability we've made to do. So this is like what we're going to show you next year. Right now, there's a small bit of empirical progress on this that George spoke about in his talk. I won't repeat it here. So we're just getting started. Yeah, this is the heaviest part of the talk, and I've not left myself enough time to do it properly. So let me think for a moment about how to do this. Okay, so when I introduced susceptibilities in the first talk on Tuesday, on SLT anyway, what I said was you're going to wiggle the data distribution and see how the posterior distribution over parameters responds. Okay, which you could think of as the Boltzmann distribution. This is like taking an external field in the physics setting and watching what the Boltzmann distribution does. So
you change the data distribution.
yes. Okay, so you can take that simple sentence and turn it into some complicated mathematics, which nonetheless is, I think, a very helpful way of framing that idea such that you can see an obvious next step. So the way you can frame this mathematically is to say, here's the set of possible true distributions. So sets of distributions often form things called statistical manifolds. So the left-hand side here is some statistical manifold of, for example, all possible distributions over sequences, right? So there is, in fact, such a statistical manifold associated to any tokenizer, which represents all the language distributions you could put on that sort of set of tokens. The actual true distribution from which you train, say, is some point. Likewise, you can take the parameter space for your model, say W, and think about all the possible posterior distributions you could put on that associated to all possible true distributions. Those are points in a manifold of positive smooth densities, which is infinite dimensional, but it's like a nice infinite dimensional thing for the Frechet manifold. And so there's a map that says, if you tell me what the true distribution is, say over sequences, here's, I mean, putting aside the role of data, so this is like the quenched posterior associated to the infinite data limit. Here's a posterior distribution which says which of the parameters are like better for that particular true distribution. Okay, so that map is F. Wiggling the data distribution is formally a tangent vector in this statistical manifold. Wiggling the posterior is a tangent vector in this Frechet manifold, and there's a tangent map to F, which says which particular direction you move in this space of densities, of posteriors, if you move the data distribution. Now, this is not an object that goes in a computer, but there are natural sort of coordinates on the space of Frechet manifolds, which come from just integrating against a function. So if I give you any function phi on W, you can take the expectation value with respect to some density and get a number. So given a list of functions, phi 1 through phi r, I get R maps from this space dens to R and just accumulate them all together. And now I've got a map from the space of densities to R to the R. Okay, that's what I've said down the bottom. So R observables give you a map from, oh, I'm sorry. Yeah, well, this is correct, but this is the composite. So I take F and then I compose with the map that sends a posterior distribution, very complicated object, lots of information. I throw away most of it and just keep the expectation values of some operators. Those could be moments, for instance, right? So if you think about Stone-Weierstrass, the space of smooth functions here, I could take some dense subset consisting of some polynomial functions. That would be like a reasonable candidate if you truncated it for what these observables might be. Or you can take other things like the ones we've discussed this week. Yeah.
What's the structure of the Frege manifold? Like fibers over distribution?
It's a locally convex topological vector space, which is complete and like locally modeled on, sorry, a Frege space is a locally convex topological vector space, which is complete and has a translation invariant metric. Well, its topology comes from a translation invariant metric. The Frege manifold is something locally modeled on that in the same way that a manifold is locally modeled on Rn.
How does it relate to like each of the individual distributions that you can have posterior? Like you said, it's all posteriors over all data distributions.
Yeah, so the posterior is something associated to a data distribution. So I think I'm confusing you by referring to this as a space of posteriors. That's inaccurate. It's a space of densities. So just positive, smooth functions which integrate to one. That space of densities is a Frege manifold. And to a data distribution, I can associate a density by taking the Bayesian posterior. Thanks. Okay, so if I have my R observables, I get a map from here to R to the R, which just gives all the values, the expectation values of those observables. Composing that is a map from D to R to the R. And susceptibilities are just the tangent map of that natural object. In particular, this rainbow serpent is just what I get if I take a point cloud of samples on the left and send it over to the right, where lowercase r is 16.
Maybe I'm completely wrong here, but I know that you measure basically this dependency on variables using the Fisher metric or Fisher matrix. Is there any link with that, or is it just a figment of my imagination?
Yeah, very nice question. So the Fisher information metric is what you use to basically make sense of flows here. So there's a way of talking about, I mean, in like a quantum information setting, you have exactly a space like this. And this is where you talk about renormalization group flow, moving around in here by putting a metric on it derived from that. Yeah, so thanks for the question. So this is like a set of ideas that's quite common in some parts of quantum information theory and like various parts of quantum mechanics. Okay, so I want to introduce that because it allows me to state in a very simple, if somewhat abstract way, what it means to control the development of internal structure if you sign on to each one of these kind of points of view that I've elaborated over the course of the talk. So if alignment is about generalization, and generalization is grounded in internal structure, and internal structure is something you can infer from tools like susceptibilities because it is related to internal geometry. Susceptibilities are expectation values. And so that means that if you can control the expectation values, if you take enough of these observables and you have enough samples and all of that, you are basically, by those hypotheses, controlling the internal structure, which leads to generalization, which is the core thing you want to control for alignment. Okay, so all of that means be here and not here, or some notion of here. right? Because these expectation values, if you just think of them as coordinates on this Frechet manifold of densities, then moving in that space is like encoding or attaining desired constraints on expectation values, which means constraints on structure, which means constraints on how the model generalizes. Now, the particular form of the constraints, so this is, we haven't done this yet. This is just like this, I'm outlining the idea that we're pursuing and why we're pursuing it and why we think it's reasonable. The particular form of the constraints might be more complicated than this. There's no reason it has to be just a single expectation value and an inequality, but this is like a motivating example. Oops. Okay, and so the idea is that if you have this point of view on what controlling internal structure looks like, you might be able to use the information you have about internal structure to direct the learning process by, for example, filtering the data, directing gradients to certain parts of the model, etc. Okay. Now let me answer a few kind of natural questions about this and then wrap up. I think it's natural to ask why expectation values. I think I just explained this first point. Of course, this looks a lot like the idea of just training a network, right? But it's different because of this U versus V thing I was talking about earlier. Just getting to low loss, there are many points with low loss, which may achieve that low loss in essentially different ways. And from our perspective, this is the root of the problem, right? You can't actually get the behavior you point at because there's many ways of getting low loss on the data you collect, and it may not be the way that you intend. So how do you get back to the golden situation where like you get something you understand and it does what you intend? Well, maybe you just allow yourself to select among the points with low loss, those that have the good structure versus the bad structure. You can't do that just with the loss, but if you buy that structure is related to expectation values against the posterior, you can do it by steering the posterior. And so if you just trade in the parameter space for an infinite dimensional Frechet manifold, it's all easy. Okay. So we're pursuing some early steps in this empirically with Edmund Lau, and so hopefully we'll have results on that over the course of the next year. This obviously has two very difficult problems encoded. So this is not like not done, right? There are two very difficult problems here. The first is, can you actually turn the things you want in what, like, first of all, can you figure out what you want? Can you frame that in terms of structure? Can you make sure those things are expressible in the language of expectation values? Secondly, can you actually effectively do this process over training, turn compute into satisfaction of these constraints? If you can do both of those things, this is our vision for how the work we're doing translates into breakthrough progress on shaping model behavior under one. Thank you. I think we have some time for questions. Yeah.
Thank you. So for me, alignment has a lot to do with humans, like different participants of, say, for medical AI. So how do we work into, say, patients and organizations, healthcare officials to bring that angle into the alignment? It's not just machine learning.
Yeah, absolutely. I think that's where this, I mean, obviously there's many components to that, but like the small piece that I'm sort of touching on, it seems to factor into this first point potentially, right? Like if you want to say, I mean, one example of an expectation value might allow you to say the model does not make use of a certain correlation in the data to make its prediction. So if you figure out how to translate that data into something that is an expectation value against the posterior, then you could aim to both measure it and maybe prevent it. Yeah.
I'm not thinking about if you have a patient group, how do you translate their language in narratives into your susceptibility or this language? How encompassing your possibilities of human desires?
I don't know. Yeah, thanks for the question. Yeah. Maybe your group can figure that. It's a question.
Um,
Do you think about like capabilities in scaling labs and if like insights from SLT could help them scale, and or is it more like there's a bunch of like AGI local minima and they don't care and they'll just get to it without SLT or something like that?
Yeah, it's a good question. So we've thought about this quite a bit. We have a dual use policy internally, which, I mean, I think it's very difficult to think about this question fundamentally. So people have thoughts about it, please come and tell me, but I have attempted to think about this quite hard and spoken to a bunch of people about it. Mostly this translates in terms of our policy internally into just being very deliberate about what we do and what we say and when, and at least articulating the reasons why a given piece of work should be shared and when and with who. I think fundamentally, it's quite difficult to move the frontier of performance. And so my assessment at present is that if you're aiming at things that are making that a more controlled, deliberate thing, then probably that is an expectation, like a good thing to be pushing. I think there's also a risk of, because one is concerned about that, not trying hard things, which may actually be a prerequisite to solving the really hard problems. So I think it's a very thorny issue. I don't pretend to have like a really great answer to this question, but yeah, definitely patterning is the stuff we're doing, which is closest to potentially enabling, if frontier model progress gets stuck, getting it unstuck. Also, it seems like it is the best thing we can imagine for solving the problem. Yeah. There's a question behind.
Is the problem with scaling the susceptibilities work to like much larger models just compute, or is it also like the technique that isn't as stable, or you don't really know if it fully converges to the right thing?
Oh, well, but even with the LLC, which is the thing we've had the most experience with, as we were discussing, it's unclear if it's converging to the real thing. So I think this is a pervasive problem. But on your first question, it's a bit of both. So we have two sort of versions of susceptibilities, right? So there's this version where we're using components and a version where we're using sort of samples. And the version with components has the disadvantage that you have to sample for posteriors for each component, which means that the more components you do, the more expensive it is. This is like still pretty tractable for up to, as I showed you, 1.4 billion. And there are pretty clear theoretical paths to replacing there's Dirac distributions in the formula. That's what creates this. There's pretty clear paths towards trying approximations to those Dirac distributions. I mean, they're limits of some distributions, and you can just try and use one of those, which would potentially obviate this. It's an open question whether that does or not. We wanted to at least find a signal first before we attempted to do any of these things focused on scaling. So once you have a situation like that, or you can just subsample the components rather than using all the components, then it's a question of just, can you approximate posteriors in very large models in a way that continues to give you the good kind of information? Can you get hyperparameters successfully? But there, our experience is basically that, like, whatever makes neural networks able to be trained seems to nobody understands this, right? We seem to be in a similar situation with SGLD-based estimation of structure, where, it was Susan Wei's idea originally to use SGLD to do this. My first reaction was, no, that can't possibly work. Like, SGLD is this stupid thing. It can't possibly have the information that MCMC is getting in the smaller models. But we did it and it worked. Why is, I think, one of the most important open theoretical questions in this area. So yeah, I suppose if that miracle continues, and maybe it's correlated to the miracle of larger models being trainable, then we're in good shape. But it could conceivably be that we get up to 1.4 billion. Pretty sure we're going to be able to do up to 10 billion. Maybe something really goes drastically wrong, and like the situation with estimating structure from SGLD diverges from the sort of niceness of the lost landscape for training in larger models. That's certainly possible. I guess at this point I would find that extremely surprising, but it's possible.
I could see a world where instead of, so it seems kind of like not straightforward to say, okay, first we're going to find the internal structure of the model, and then we're going to see if that makes sense, and then we're going to develop a new training paradigm. When you could just say, okay, we're going to figure out the internal structure of the model, figure out the parts of that we don't like, and directly modify the model.
Mhm.
So is there a justification for, instead of doing the more direct route, going through the patterning thing?
Oh, sorry. Yeah. I mean, I guess when I say patterning and learning process, I have in mind, yeah, thanks for the question. Like also fine tuning and so on, not just like training from scratch. That's right. Yeah. I guess to more directly answer your question, certainly it's a much bigger lift to get everybody to change the way they do pre-training, right? And so one would have to very clearly demonstrate the alignment benefits of this in more controlled, smaller settings like post-training or fine-tuning.
Maybe two related, two possibly related questions. So the first one is which observables are you maybe most excited about? So I mean, with susceptibility, you think bring the most signal, maybe including things that could be learned through other interpretability methods.
Yeah.
And maybe more ambitiously, when you're talking about programming the posterior, like in what language are you?
Easy questions. Yeah, so the first one, I'm really interested in mixing this with like more activation-based methods of interpretability, where, yeah, I mean, for instance, you could do this with SAE features, or any other kind of thing that's based on activations. There must be some profound link between, say, activation geometry, feature geometry, and lost landscape geometry that you could potentially infer if you go in that direction. Some folks from Anthropic were interested in thinking about that. We haven't done any work on that, but I think that's one of the most interesting sets of observables. Beyond that, I haven't really thought about it. I think this is, it would be very strange if the first sort of sets of obvious observables were sufficient for the task. Yeah. So I don't mean to suggest that the observables we're doing right now are like a sufficient foundation for the more ambitious story of patterning. Yeah, definitely. One of the things that has to be done is systematically exploring other kinds of observables. I mean, this is physics does this all the time. For the second question, well, I think Tom already answered this question. Yeah, I don't know. I think this is a very deep and important question, and I put the word language here for a very precise reason. So there is like some candidate stuff floating around in mathematics that sort of talks about the kind of acquisition and change of structure in geometry that we're talking about here. But I think it's mathematically very underdeveloped relative to the scale and complexity of the kind of geometry we're talking about. So I would hesitate to answer this question except to say there's clear directions to go. It seems fundamental, and in the longer term, this is like what the science of patterning probably needs. Seems like we're done. Thanks, everybody. I did want to say that I'm visiting Watanabe in October, as I said on the Discord, and I want to like embarrass him by showing him a photo of like everybody who thinks he's really great, because he's like super modest and like hiding in Japan, and he's very hard to get to and talk to. And like I really want him to know how amazing and beautiful the work he did is, and how many people are finding it profound and important. So if you want him to see you smiling at him, shall we take a photo over there right now?
Does anyone have a copy of his book so we can like hold up?